So we're going to start today with the first topic from the course, and it's on sets and set theory. And some of the topics in here will probably sound familiar to you or look familiar to you. You've probably seen it at some point in your math education in the back, in your past. But I'm going to present the lecture as if this is new to you. So. And we will stop quite frequently along the way, and I'll ask you to answer some questions and make sure that everyone's on board. Before we get to the lecture for today, there was a question asked: are we going to be staying in the same group for our projects, or will it be different every time? And the answer is, my intent right now is that it's going to be different every time. And I'm just going to let the system itself randomly assign you to groups, and so that you'll have the opportunity to work with probably everybody in the class at some point. I get this so it's as big as possible, but still centered in the. Smaller. All right, so you're going to see a lot of definitions in here to begin with. I do want to remind you that all of these notes that you're seeing here are notes that are available at the online site and using today's date. So we're going to be talking about sets, and so let's start off with a definition. A set is a collection of distinct objects, and the objects are called elements or called members of the set. A lot of times in math, we use letters or numbers to represent elements, but we can also use symbols and various other things. We can even use entire words as being elements of a set. We never list an element more than once. Once it's in there, it's in there. So we would say that the set A, B is equal to the set AB. So the only distinct elements of this first set are A and B. So really we would say this set is equivalent to this one because these two also have the same two distinct elements, even though the A is written 3 times here. These are carbon copies of one another. That's what this little statement here means. If an element does appear more than once, we just rewrite it in its simplest form with the fewest characters possible. There are 3 different ways that we represent a set, and it's very important when they ask for a set that you don't just write the elements of the set. So a lot of times if you wrote the answer was AB, let's say that this was the answer. This was the answer AB. This we would say the set AB, whereas these are 2 elements of the set A and B. And so if you just wrote the answer with A comma B, it probably would mark it wrong on the system because it expects you to have the curly brackets around it. So if they ask for a set, give them a set, and that means put the brackets around it. We can describe a set in words, and as you can see, as you go along each one of these rows, there's different ways to describe a set. The first one is just to say the name of the set in words. Describe it as a sentence. B is the set of members of the Beatles in 1963. Now the roster method, just like when I see my class roster, all of you are listed. In set notation, if you're going to do the roster method, then you're going to list all of the elements. And so the elements in this case are the 4 Beatles: George Harrison, John Lennon, Paul McCartney, and Ringo Starr, each separated by a comma. Now the set builder notation is kind of more mathy, and it pretty much uses the same as uses the word description in the set builder notation, but it has this symbolic piece in there. And the way we interpret that is that the set of all X such that, so we're using a variable, the set of all X such that X is a Beatle in 1963. Here's another example. And I think because I wrote on this, it's it's focusing in on my writing and not on the other text. So I'll have to think about that. The states that begin with A, set builder notation, very similar. The set of all x sets at x is a state that begins with A. In your homework, you'll be asked to go through each one of these methods. If you're given the set in the description form, translate it into the roster form. If you're given a set in the roster form, translate it into the set builder notation. So be able to go back and forth between all of these different representations of a set. The roster method, we would list all of the sets that, all of the states that begin with the letter A. Okay, more terminology. The empty set. The empty set is the set that doesn't contain anything. And sometimes we just write it like this. This is our notation for a set, but there's nothing in there. So it's sometimes called the null set, N-U-L-L. And the other individual character that we use sometimes to represent the empty set is the little circle with a line through it. That also means the empty set. So these two are equivalent. And I know I said that usually we write sets with the curly brackets around it, but just this character by itself means that it's the empty set. We're going to start talking about Venn diagrams here very shortly. And a Venn diagram, we write a rectangle that represents, in this particular problem, we call it the universal set. All of the elements that are under consideration in this problem. And then we represent sets with little circles inside the rectangle. So this is a set A. The universal set in this example contains the elements A, B, C, D, and E, and you can see them all five of those elements there, A, B, C, D, and E. But notice none of them are in set A, in the circle A. Since no elements are in the circle A, we would say A is the empty set. And we can write it in either of those two versions. Okay, more symbols. We have this symbol. It looks like an E kind of. And a lot of times in mathematics, we use individual symbols to substitute, take the place of an entire phrase of words. And so what that symbol means, and every time we see it, we're going to say is an element of. So if I use this example right here, I could say A is an element of the set U, the universal set. And I would write it in symbols. I think the hardest part about this whole section is just understanding the symbols, what they mean, the differences between them. And we would say something like this. The letter Z is, if you put a line through that E, it means is not an element of. Is not. Many of the problems that they ask you to do in this section, they'll assume that you know about our number systems. And at some point in your math education, you probably heard about these number sets. And so I included them down here. I also included them, you're not going to be able to see both of these, but so I guess I'll just show them one at a time. All right, so here are 1, 2, 3, 4, 5 different sets of numbers that we use frequently in mathematics. And the first set, N, corresponds to the natural numbers. And so the natural numbers, I'll just describe it down here. Instead of, you have a description here of what we're talking about with these natural numbers. This is really the first set of numbers that children learn. It's the counting numbers. And when students count, they don't start with 0, they start with 1, 1, 2, 3, and so on. So the natural numbers are these. So, and it goes on forever. We say that this is an infinite set because the numbers go on forever and ever. The whole counting numbers starting with 1, That's the set of N. And you'll see where these come in when we start doing some problems a little bit later. One that's not there is W, and I'll write the name. This would be the whole numbers. And the whole numbers include all of the natural numbers, but plus the 0. So if they use the whole numbers at all, it's the natural numbers plus the 0. That's one that doesn't appear in this grid. The Z, that's the set of integers. And so for the set of integers, we have the counting numbers, or the whole numbers, all the positive ones that go on to infinity to the right, but we also include the negative numbers in the set of integers as well. So it's really a set of numbers that goes from negative infinity to positive infinity and jump by 1. That's the set of integers. Q is the set of rational numbers. Well, I don't know how to write these in roster form. So think about anything that can be written as a fraction. And you got to expand your definition of a fraction, because fraction includes all of the integers. So this number -3 here, it doesn't look like a fraction, but you can write it as a fraction. If you write, say, -3/1. Since it can be written as a fraction, it's included in the set of rational numbers. But the set of rational numbers also includes numbers like 1/3 and 1/4 and 1/5, all of the unit fractions, 2/3 and 2/5, and so on. All of the fractions that you can possibly write where you have an integer over an integer, except you can't have a 0 in the bottom, because that would lead it to be undefined. I can't list all of these, so I'm just going to go with their definition. Q with the little c on it. You'll see later that when that c is a superscript like that, it means the complement. That means the non-fractions, anything that's not a fraction. All of the numbers that can't be written as fractions. If Q is a set of all those numbers that can be written as fractions, then Q complement is all those numbers that cannot be. It's the opposite of, you can think about it. We call it the complement, because opposite has a connotation in math to mean negative. So we can't really write all these out in lists, but just to give you a sense of some of the numbers, they included some in here. Like if you just wanted to do square roots, you could do square root of 3, square root of 4, but not the square root of, or square root of 2, square root of 3. You can't do the square root of 4 because the square root of 4 is 2. And 2 can be written as 2/1, so it's rational. So therefore it can't be irrational. Think about it this way. If you took all the rational numbers and all the irrational numbers and you put them together, then you'd have the set of all the real numbers. So in a Venn diagram, you would really just kind of split this right down the middle. If this is the set of real numbers, you would have the rationals on one side and the irrationals on the other. And together those form all of the real numbers. You know, you can do cubed roots, cubed root of 9, cubed root of 12, but you can't do the cubed root of 8, because the cubed root of 8 is equal to 2, and that's a rational number. Some of these transcendental numbers like pi and e, those are also included in the set of non-rationals or irrational. Okay, so I'm just sharing these with you here because when you see them in your problems later on, you're going to say, oh yeah, I remember that stood for this set of numbers, and then you'll want to refresh your memory as to what those numbers are. Take a look at number 41. Now they want you to say if this is false or true. And if it's false, explain why. This one says, Ralph is an element of the set containing Ralph and Alice and Trixie and Norton. Is that a true statement or a false statement? All right, go ahead and write your response in the chat, and then I can see. The next time I'm going to ask you to do it a slightly different way. Now, most of you are replying to everyone. That's fine. If you're if you don't want to do that, I understand. You can just send it to me only. Now, it is possible for students to look at what everybody else has written and just write that answer, right? So here's another thing we can do. I'm going to ask you to do another one here in a second, and I want you to write your answer in the chat box, but I don't want you to hit enter until I tell you to hit enter. That way we'll see everybody's answer all at one time. And I'll count it down, 3, 2, 1, hit enter, and everybody will write their answer at one time. All right, here's 49. It's either true or false. This says the set 5 is an element of the set containing the set 5 and the set 9. Okay, true or false, without hitting enter, write your answer into the chat box. And then I'm going to count it down. You can see, you know, there might be 20 problems in this section, but you can see some of them are going to go pretty quickly. Okay, here we go. Type your answer in, and on the count of 3, I want you to hit enter. 3, 2, 1, enter. Okay, got a lot of trues and some falses, a couple falses in here. Okay, but mostly true. And you are correct, most of you, it is true. The element here is the set 5. And notice that that whole element is inside the set. And since the set 5 is in the set, 5 is an element of that set. Okay, continuing on. We'll keep coming back to problems that I think that you're going to be doing. On one of the worksheets, if I can magnify this a little bit so you can see it. You can see it gives additional examples of all of the different number systems, plus some examples. Negative integers, negative 17, negative 3, 0, positive counting numbers, whole numbers with some examples. A lot of times they don't give you all of them, they just give you some of them. All right, cardinal number. What is the cardinal number of a set A? Simply what that means is that how many elements are in the set. The number of elements in the set is the cardinal number of the set. And here's our notation. The number of elements in the set is n of A. I say n of A. Okay, here's a set B. B contains the elements X, Y, Z, star 1, 6, 5. So a lot of times we use numbers and letters to be elements of sets, but we can even use symbols as well. So this notation here means what is the cardinality of the set B? Said another way, how many elements are there in the set B? Go ahead, enter your answer into the chat. Very good. You guys seem to be picking this up. Count them up. There are 7, and so the answer to that one is 7. No set, it's just a number. Okay, the next idea is what's the difference between equivalent sets and equal sets? And the short definition is this, that 2 sets are equal if they have the same number of elements. And that's why we did this cardinality thing here, because we need to know the number of elements. The 2 sets can look completely different, like 1, 10, 100, 1,000, 10,000. These are powers of 10. The number of elements in C, 1, 2, 3, 4, 5, 6, 7. 7. When you have 2 sets that have the same number of elements, even though those elements don't match at all, well, here they match on the number of 1, but the elements are not exactly the same, all exactly the same, but they have the same number. We say that B is equivalent to C, you know, or we can, and the equivalent sign that we use is just kind of this little squiggly. And we would say B is equivalent to C. A lot of times we mistake them, and we use the word equivalent in a lot of different contexts. And many times it means the same thing as equal, but it doesn't mean the same thing here, because equivalent just means the same number of elements. Now, if you have equal sets, and that's another definition, 2 sets are equal if they have all the same elements, exactly the same elements. Now, they don't have to be listed in the same order, But we would say here that B is not equal to C. They're equivalent, but they're not equal. They're not equal because they have different elements. So you see the difference? You're counting on one to determine equivalence, you're counting the number of elements, and then you're matching them element for element and making sure that they're exactly the same for equality. As an example, I can give you the set A, which is equal to 5, -3, 8, 0, and 11. And I can give you the set B, which is -3, 0, 5, -3, 8, and 11. And generally in a problem like this, you're going to be given two sets, and you're going to ask, are A and B equivalent? Are A and B equal? Are they both, or are they neither? And there's 4 different options that you can choose from. Okay, this time, write in the chat one of these 4 words. Equivalent only, equal only, both, or neither. When you're ready. Equivalent only, equal only, both, or neither. And I tried to give you a tricky one here because you may notice that -3 is an element that I wrote twice in B. And remember, we don't write these duplicates. So another way to write B is just to write the element -3 one time. Okay, neither, 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 equivalent, neither, equivalent, both, equal. All right, so those of you that answered neither, after I gave you that little hint, you still want to answer neither? Okay, the most recent responses are both. So some of you are switching answers, which is fine. Okay, the number of elements in A is equal to 1, 2, 3, 4, 5. The number of elements in B, notice we made it a little bit more efficient by writing the -3 only once. So these two are the same. We're not going to doubly count the -3. So 1, 2, 3, 4, 5. B also has 5. And because they have the same number of elements, we know that they're equivalent. But not only are they equivalent, you can match 5 for 5, -3 for -3, 0 for 0, 8 for 8. Not only do they have the same number of elements, but those elements are exactly the same. It does not matter that they're listed in a different order. So we would say A is equal to B as well. And since they're equivalent and equal, the correct response is both. This whole notion of what I did here was link them up one item for one item, like this. We would call this a one-to-one correspondence. And so they formally define that here, although I don't think they're going to talk much about it in the homework. If set A and B can be placed into a one-to-one correspondence, then A is equivalent to B. If they can't be put into a one-to-one correspondence, then they're not equivalent. And then here's our definition of equal. And the next definition is finite versus infinite. And one way that you can define finite and infinite is based on the cardinalities, based on the number of elements. So if the number of elements is infinity, if the number of elements in A equals infinity, that is, there's an infinite number of elements in A, like the natural numbers, like the integers and so on. If this is the case, we say that A is infinite. If the number in the set, the number of elements in the set is less than infinity, you know, could be a billion, a trillion, a quadrillion, a quintillion, or 1, 2, 3, 4, anything that's a finite number, if it's less than infinity, then we say B is finite. Let me give you another set. C equals 1, 2, 3, 4, 5, and D equals 1, 2, 3, 4, 5, comma, dot, dot, dot. And that dot, dot, dot means that it goes on in the same pattern forever. We would say, since the number in C is equal to 5 elements, we would say that C is finite. And D, we can't possibly count up all those numbers because they go to infinity. And so the number of elements in D is equal to infinity, so therefore D is infinite. Finite and infinite deals with the number of elements in the set. Okay, just checking the chat just to make sure, and I have to scroll through because there's a lot of answers there. I just want to make sure that I don't miss any questions if you have any questions. All right, so now we're going to get into some of our set operations. Now, you know a lot about mathematical operations. For example, we have the arithmetic operations like plus and times and minus and divide. And if you want to add two numbers, if you want to calculate the sum, we use the addition operation and we take one number and add the next. And we have a similar definition for subtraction. You need two numbers, or division or multiplication. Those are the operations, the basic operations for numbers. But if you want to talk about similar operations for sets, it also involves two sets. So, usually, not always. All right, a couple of definitions up here. You have the universal set U, and then you have set A and set B. A and B do not overlap in any way, so we say that they have no elements in common. An example for this would be if A was 1, 2, 3, and B was A, B, C, like that. Those two, you'd put the three numbers in one set and three letters in the other, and notice that there are no elements that are common to both. So we would say that these two sets are disjoint. Disjoint. And all of these are Venn diagrams. So we're going to start drawing Venn diagrams quite a lot. Proper subset. I'll talk about this more in a little bit, but we say that A is a subset of B. A is completely contained in B. An example for this one would be if A was the set 1, 2, and B was the set 1, 2, 3, 4, 5. Now B is the outer circle, so it contains everything inside B. So 3, 4, and 5 are inside B, but also 1 and 2 are inside B. So 1, 2, 3, 4, 5 are all elements inside B, but the elements 1 and 2 are also in A, so they go into the inner circle. And you can see all of the elements of A are also elements of B. So if that's the case, we say that A is a subset of B. A is a subset of B. Here's a Venn diagram, and notice for this example, A and B overlap, so that means they have something in common. So just as an example, I'm going to define the set A with all of its elements. Just be careful here because A contains X and Y, but it also contains these elements over here in the intersection, in the common area. So A is X, Y, Z, and W, and B is A, B, C, but also Z and W. And notice that these two sets match on Z and W. So Z and W are part of this common area here, and this is known as the intersection. And the character that we use for that, the operation that I talked about earlier, is the upside down U. So for this example, we would say A intersect B. What's in the intersection? What's common to both A and B? That's our definition of intersection. And then we would write down Z and W. Those are the elements that are common. Those are the elements that are in the middle area there. And we've already talked about equal sets, but I've given you an example of each of these. And so I'll give you an example here. And just to see that you can write them in different ways, I'll change the order. But you can see that each of those two have a 6 and a 9 and a 7. They have the same number of elements, and those elements are exactly the same. So we say A is equal to B. Is A equivalent to B? Number in A is 3. Number in B, 3. So A and B are equivalent. If you're looking for generalities here, if you do have two sets are equal, then they have the same exact elements. And if they have the same exact elements, they have the same number of elements. So all sets that are equal are also equivalent. But we can't say the opposite. We can't say the converse of that. We can't say all sets that are equivalent are equal, because that's not true. But if two sets are equal, then they are definitely equivalent. The next definition is the complement. Just so you know, the complement of a set is not like a compliment that someone would pay you, like, gee, I like your new shirt. That's a compliment. And complement is spelled with an I. But they're very similar otherwise. Complement of A means not A. So in order to identify the complement of a set, you need to know the universal set. Now, some books use the apostrophe to mean complement. Our book uses a little superscript C, a complement. So that's what I'm going to use. So it's consistent with what you see on the Newton Alta site. So in this section, wherever you see an apostrophe, that means complement, but also the superscript C also means complement. So if we wanted to graph A complement C, and here was set A, and here was set B, and then this whole thing is the universal set. I'll label it with a U. A complement means all of those elements that are outside of A. So as a graph, or as a shading, if we wanted to shade the Venn diagram, it would look something like this. The only thing I'm not going to shade is anything inside the A circle, because complement means not A. So I don't want to include any part of A. And it would look like that. Some of B is shaded, but the fact that B is in this diagram is irrelevant. It's not needed here. So we just act as if it's not there. Now let me give you an example where we're using specific sets. So let's say that A is the set 1, 2, 3, and B is the set X, Y, Z, 3. Now 3 is common to both, so I'm going to put 3 in the middle. A also contains 1 and 2, so I'm going to make sure that 1, 2, and 3 are in the circle A, and that 3 is in the intersection. So I see it's common to both. B contains the 3, but it also contains X, Y, and Z. And this is the universal set. All right, so if we wanted to identify a complement, one way you can do it is just to list all of the elements, but take out the elements of A. So just cover up those elements there. And everything outside of A then would be the complement. So the complement of A is X, Y, and Z. Now here's another way you can do it. If you say the universal set is 1, 2, 3, X, Y, Z, because you see 1, 2, 3, X, Y, Z and nothing else in this diagram, if you wanted to calculate a complement, what you do is you just go strike out of the universal set these elements 1, 2, and 3. If you take out 1, 2, and 3, what are you left with? X, Y, and Z. Okay, I want you to write the answer to B complement in the chat. Be very careful how you write it, but what is B complement in this example right here? All of those elements in the universal set that are not in B. Okay, everybody have a chance? I see some correct answers. I see some incorrect answers. It turns out that if you just write 1, 2, we're going to have to mark it wrong because it's a set. And the set requires the set notation with the curly brackets around it. And so I know what you meant. I know what you're conceptually thinking is correct. But just so you know that in Newton Alta, they're really going to want those curly brackets because B complement is a set. So you have to tell it somehow that it is a set. Okay, very good. And then I noticed one nice answer up here. Wesley had B complement. That was impressive. B complement with the apostrophe, because it's probably hard to write a superscript C in that case. So, okay, very good. That's complement. Okay, we talked about intersection. So what I want to do is go back and give you some examples of intersection specifically. And as you know how math works, the first couple of examples are pretty straightforward. You're just using a definition. So you're stretching there, Kayla? Raising your hand. Okay, here's our next example. A intersect B. And first time you see it, I'm going to write it out in words so you know how we say that mathematical statement in words. A intersect B. You're looking for elements that are common to A and B, and so if you just shade it, it's this middle region here. Now as an example, and we'll do our example over here. Let's say A is 2, 4, 6, 8, 10, and B is 0, 3, 6, 9, and we'll stop there. Okay, so put all of those numbers in the Venn diagram and then calculate A intersect. Your problems in Newton Alta will be similar to this. In the last two sections, you're doing a lot of work with Venn diagrams. And so you'll be asked to do problems like this where you take a set apart and insert its pieces. Sometimes you'll be given the Venn diagram with the pieces inside it already, and you'll be asked something related to the Venn diagram. All right, looks like they match on the 6. And that's it. So 6 goes in the middle. And then we have 2, 4, 8, and 10. Notice I didn't write 6 twice. But since A contains the elements 2, 4, 6, 8, 10, you have to have those 5 elements inside A. I put 6 in the intersection because I know 6 is also in B. But B also contains 0 and 3 and 9. So you have to look ahead and you have to figure out what's in the intersection and then draw the sets accordingly. Okay, so thumbs up or thumbs down? Remember where the thumbs down is? thumbs down is over in the participants, one of those buttons over there, and it's in the dot, dot, dot. So if you do the dot, 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 you can have thumbs up, thumbs down. Are you going to give a thumbs up to this answer or a thumbs down to that answer? Go ahead and select one of those reactions. Do you see it? Let's see if I can do it. There's the down, and there's the up. I've got 11 ups and 3 downs. Well, I'm going to go with the minority here and give it a down. Not because 6 is incorrect, but because it doesn't have the curly brackets around it. All right, we'll continue to do this until I get more corrects than not correct because of that answer. Just remember to put the brackets around it. The next operation, remember, plus, times, minus, divide with numbers. Sets have operations too. Complement, intersection, and this third one, which is union. A union. And a union is like you're going to take all the elements in one set and all of the elements in the other set and just combine them together. And the last thing that's optional is to get rid of the duplicates. Think about this, the union as, sometimes they refer to marriage as a union between two people. And so if the one spouse has a group of friends that they want to invite, and the other friends, the other spouse has a group of friends that they would like to invite, then what you're going to do is you're going to invite everybody from both friends lists. And there might be some duplicates because people who are going to get married probably have a lot of common friends, but they don't want to send an invitation twice to the same friend. They're just going to send them one. So putting all those folks together and asking the question, how many people attended or who are the people that attended the wedding, that's like the union. And you don't want to do the duplicate. So let me flash over here to give you an example. A with an upside down, or like a right side up, I should say, U, is U for union. And we say A union B. That's how we say that. It's everything in A and everything in B. And we're also going to include all of those elements that happen to be in both A and B. All of the bride's friends, all of the groom's friends. It's a heterosexual wedding. Common friends in the middle. All right. Let me just use the same example I used above. So you can actually use the same Venn diagram up here for this problem. And what is, in this example, A union B? Don't forget the curly brackets. So just take all the elements and just start writing them all. And if you run into a duplicate, don't write the duplicate. So you have all the elements in B, doesn't matter the order in which you write them, and then you have all the elements in A as well. I'm not going to write the 6 twice. The Venn diagram doesn't look any different than the one above, but for a union. All right, so here's what students do sometimes. They confuse the intersection and the union. And this would be equivalent in numbers if you wanted to add 7 plus 3 to get 10 and you got 4 as the answer instead. That is, you applied a subtraction operation when the operation called for was addition. So they're two different operations and they mean different things. And sometimes it's just a matter of getting it correct. Does that mean that we're looking for commons, or does that mean we're looking for just all the elements together? One example now, I'm not going to give you these sets. I'm just going to put some things into the Venn diagrams. I'm going to ask you some questions. So here are the questions I'm going to ask. What is A complement? What is A intersect B? What is B union A? And here are the elements. Let's do E, F, G, H, K, M, N, P, Q. Okay, here's your example. And based on what you see in the Venn diagrams, write down the answers to each of those 3. 1, 2, and 3. Yeah, I'm not sure. You can use the complement. Yeah, you can send it. Go ahead, Chloe. That's fine. I'd like to see the answers. So A complement first. And once you get A complement done, then go on to A intersect B. I don't know that we have an upside down, so you might have to spell out the word intersect. So A complement and A intersect B. Now I'll just spell it out, and then maybe A union B. Yes, this is a Q, sorry. I was trying to do all letters. Maybe if I do a little, give it a little tail there. Yeah, my cursive is not that great, so this is supposed to be K here. Okay, so I'm seeing a lot of good answers. I'll just write them down here and then you can check. Here's the set A. If you would prefer to write down the elements of A, it would look like this. And B would be H, K, and M, and P, and Q. So you could write the elements of the set if you wanted to. But everything not in, I suppose I should write the universal set too. E, F, G, H, K, M, N, P, and Q. Universal set. Don't need to do that. Didn't ask for it. All right, so A complement, I'm going to cover up everything in A and just write down all the elements that remain. M, N, P, and Q. The complement, not A. Everything except those elements in A. The intersection, that's the middle piece, HK. And the union, you're going to write down all the elements that are in either A or B or both. You're going to combine or join all of the elements together. So E, F, G, H, K, M, N, P, and Q, all of them. In terms of intersection and union, there's a couple of properties that you would probably deduce without having a special property for it. But if you take the a set A, which can contain anything, and you take the intersection of a set that contains nothing, and you ask the question, what's common to both? What's the intersection? Well, since the empty set doesn't contain anything, then there are no elements common to both sets. So that also has to be the empty set. And then if you combine the empty set and another set A, which can be anything, if you take the union, you're going to group together all the elements of A with nothing. What do you have if you put those two together? Well, you have all the elements in A, and that's what this is saying.